Hello, humans, and welcome back. In part one of this series, we talked about John Dalton and the basics of his atomic theory. But in today's lesson, we're going to be diving into part two, the periodic table of elements, chemistry's very own recipe book. So let's jump right in. One of the biggest takeaways about the periodic table is that there are actually many different versions or layouts out there. But the one your teacher uses and the one you'll see on your tests, including mine, is this one right here. It was created by a Russian chemist named Dmitry Mendeleev in 1869. And the basic idea behind his design is that he organized the elements in order of increasing atomic number. That atomic number is a whole number you see at the top of each box. Sometimes it's in a corner, sometimes it's centered, but either way, it's the atomic number. And it tells you something very important that we'll get to in another lesson. What Mendeleev noticed is that when you arrange the elements by increasing atomic number, their chemical properties start repeating in pattern. And he called this trend the periodic law. And that's why the table looks the way it does. But something really cool about Mendeleev's table is that you'll notice there are a few blank spaces, and I purposely didn't color them in here. He actually left those blank on purpose because this arrangement helped him predict the existence and even the properties of elements that hadn't been discovered yet. And sure enough, many of those predicted elements were found later and fit exactly where he said they would. Now, how do we actually read the periodic table? Well, just like you'd read a book, left to right. When we read across a row, we call that a period. That's just another name for row, and there are 7 periods on the periodic table that I've labeled here. When we look at a column, that's the up and down direction. That's called a group. It's also called a family. So those 3 words, group, column, and family, they all mean the same thing. But personally, I really like the word family. Because when I teach this to my students, I always ask them the same question I'm going to ask you right now. When you think about you and your family, what kind of traits or similarities do you all share? Maybe you have the same hair color as your mom or your sister. Maybe you and your brother have the same shade of brown eyes. Maybe you're all around the same height, or maybe you and your siblings have similar personalities. So just like you share similarities with your family, the elements in the same family or group also share similar chemical properties with each other, for the most part at least. But that does not apply when you go across a row, and that's very important. Elements across a period do not all behave similarly, but elements in the same family do. Now, the periodic table is arranged into 3 main groups, and I've color-coded them here. Metals are in blue, nonmetals are in yellow, and this red staircase marks the metalloids. Before we talk about what each group is like, let's remember something important. A physical property is anything you can observe or measure without changing the chemical identity of the substance. So things like color, smell, density, melting point, boiling point, hardness, those are all physical properties. One thing I always tell my students is this. If you can remember the physical properties of metals, you'll automatically know the properties of nonmetals. Because guess what? They're the opposite. So for example, metals tend to be shiny, and a fancy word for shiny is that they have luster. They can be hammered out into sheets, so we say they are malleable. Think of something in your pantry that's a metal hammered into sheets. If you're thinking aluminum foil, then you're on the money. They are also called ductile, meaning they can be drawn into wires. A perfect example is copper wire. If you've ever seen the inside of an aux cord or a cable, you'll notice those tiny copper wires inside. And speaking of copper, metals are also very good conductors of electricity, which is why copper is commonly used in wiring and sound equipment. Also keep in mind that most metals are solids at room temperature. And I say most because, for example, mercury actually likes to exist as a liquid at room temperature. Now for nonmetals, again, the complete opposite. So for example, nonmetals are poor conductors of electricity. In fact, they usually serve as insulators, meaning they stop electrical current from running through. They tend to be brittle, meaning if you try to shape them, they're going to break apart instead of flattening like a metal would. They're also dull, so they don't have luster, and they're usually liquids or gases at room temperature. However, and I always point this out, that even though most nonmetals are actually gases like oxygen and nitrogen gas, some nonmetals exist as solids at room temperature. And two great examples are sulfur and phosphorus. And then we have the metalloids, which are this unique group that fall along the staircase. They have properties that are intermediate between metals and nonmetals. So for example, they have metallic luster, so they look shiny like metals, but they're brittle and tend to shatter when stressed, which is more like nonmetals. They're also often called semiconductors because their ability to conduct electricity can change depending on the conditions. So the biggest takeaway is this. Metalloids share a mix of metal and nonmetal properties, which is why they get their own special group. Now, some of these families on the periodic table have very special names, and a few of them are really worth pointing out. Starting with group 1, we have the alkali metals. The only element in that column that's not an alkali metal is hydrogen. And the reason why hydrogen is placed in that family is not because it behaves like a metal, it doesn't, but because it has the smallest atomic number, which is 1. And if you remember, the periodic table is arranged in order of increasing atomic number. So that's why hydrogen sits at the top of that column. But keep in mind, hydrogen is a non-metal. Now the alkali metals, lithium, sodium, potassium, all the way down. These are very reactive. And there's a reason why they're so reactive. But I'm going to save that explanation for another lesson where I talk about ionic versus covalent bonding. But for now, just know that alkali metals are so reactive, they don't really exist by themselves in nature. Then we move on to group 2, or the alkaline earth metals. These are also reactive, but not as reactive as group 1. Next, we have this entire middle block, this big chunk right here. Okay, these are called the transition metals. These are the metals you're probably most familiar with. Iron, copper, gold, silver, nickel, all of those. And below them, you'll notice 2 additional rows. These 2 rows are actually part of the transition metals, and together we call them the inner transition metals. The first row is the lanthanide series because it starts with lanthanum. And the second is the actinide series because it starts with the element actinium. Now, you might wonder, why aren't these rows placed up here where they really belong? And the answer is quite simple. If they were placed in line, the periodic table would be incredibly long, like way too long to fit on a single page. So we write them down here for convenience. But in your mind, imagine copying and pasting these 2 rows right into these 2 spots. That's where they actually fit. And after that, we have some families named after the first element in the group. For example, the boron group in group 13, the carbon group in group 14, the nitrogen group in group 15. Then we got group 16, which we call the chalcogens. Group 17 are the halogens, and group 18 are the noble gases. And the noble gases are considered inert gases because they really don't like to react with anything. In fact, they're the complete opposites of group 1 and 2. Instead of being reactive, they're actually super stable. And there's a reason for that, and we'll get to that in another lesson. But just so you know for now, noble gases are chilling. They mind their own business. And honestly, every other element wishes it could be like a noble gas. Heck, I want to be like a noble gas, but we'll talk more about that soon. One more thing I want to point out is the numbering of these groups. At the top, you'll see 2 types of labels, numbers 1 through 18, which are the modern group numbers, and then letters like 1A, 2A, 3A, 4A, etc. So for example, boron is in group 13, which is the same thing as saying 3A. The A groups, meaning groups labeled with an A, are what we call the main representative elements. And that's important because those groups tell us something crucial about the elements in them, which we'll get to in a separate lesson. One more thing I want to point out about the noble gases is that they are monatomic. That means they like to exist all by themselves, just a single atom. One atom of neon, one atom of argon, one atom of krypton, and so on. In fact, that's where the word mono comes in. Mono means one atom. And that's part of why they're not very reactive. They're already super stable, so they're happy existing alone. But now let's talk about something very important as well, and that's the diatomic elements. There are 7 of them, and there's a great mnemonic to help you remember. And it's have no fear of ice cold beverages, which stands for hydrogen gas, nitrogen gas, fluorine gas, oxygen gas, iodine gas, chlorine gas, and bromine gas. I always tell my students to memorize these, not just for this chapter, but because you'll see these over and over again throughout chemistry. It really does help in the long run. The basic idea is that in their natural form, meaning how they're found in nature, these elements exist as 2 atoms chemically bonded together. So, for example, chlorine gas naturally exists as Cl2. Oxygen gas, the oxygen in the air we breathe, naturally exists as O2, where the 2 is a subscript, and subscripts tell us how many atoms are bound in a molecular compound. Now, aside from the monatomic noble gases and the 7 diatomic elements, there are also a few polyatomic elements, meaning their natural form is made up of more than 2 atoms bonded together. And if it helps you, poly means many, so many atoms bound together. Hopefully that helps. For example, phosphorus usually exists as P4, or 4 atoms bonded together. Sulfur often exists as S8, or 8 atoms in a ring, and O3, which is ozone, is also a polyatomic form of oxygen. And one last thing I want to sprinkle in, just for fun before I go, is the idea that all of these elements are around us all the time. Whether this is your first time learning chemistry or you're reviewing it before a test, it's really cool to realize how often we interact with these elements without even knowing it. So for example, I love fireworks on the 4th of July, and the beautiful red colors come from strontium. We've talked about copper wire, which helps amplify sound and powers our electronics and TVs. For my artists out there who love to paint, cadmium is found in yellow, orange, and red pigments. Helium is in balloons, neon is in bright advertising signs, fluorine is in toothpaste, lithium is used in batteries, calcium is in our bones and in the shells of crustaceans. These elements are everywhere, even the more radioactive ones like plutonium, which we'll talk about in a separate video. So that's one of the biggest takeaways. The periodic table isn't just something we memorize for school, it's literally a list of ingredients that make up the world around us. And I really encourage you to do a little Google search sometime. If there's an element that catches your eye, look into it. You might be surprised at how cool its role is in everyday life. And that concludes part 2 of this lesson. In the next series, we're going to take a deeper look into the atom itself, or the Bohr model, and talk about how to find the number of protons, electrons, and neutrons. So if that's something you're interested in learning more about, definitely stay tuned for the next video. As for now, thank you so much, you guys, for listening. And if you found this video helpful, please don't hesitate to like and click that subscribe button. Help a teacher out. Thanks, guys, and see you next time in my science studio.